When it comes to wiping out entire species, humans are terrifyingly efficient. We hunted the passenger pigeon from populations in the billions down to absolute zero, while the woolly mammoth succumbed to a combination of climate-driven habitat loss and, in some regions, human hunting pressure. Essentially, history shows that if human civilization decides an organism is directly in its way, it usually vanishes. But there is a tiny creature, weighing less than 2.5 milligrams, that has been openly defying our entire technological empire, year after year. Most people assume that apex predators like sharks, lions, or venomous snakes are the most lethal forces on the planet. But if you look at the raw data, the contrast is staggering. Sharks are responsible for roughly 5 to 10 human fatalities globally every year. This microscopic buzzing anomaly, World Health Organizations estimate it contributes to up to nearly 1 million deaths annually through diseases like malaria, dengue, and yellow fever. It is, by a wide margin, the deadliest animal vector in human history. We have billion-dollar public health budgets, the most brilliant minds in world-class laboratories, and an obvious moral incentive to protect human life. Yet, here they are, flying free and buzzing right in your ear. Why is it that a civilization capable of splitting the atom is still forced to share the planet with this fragile insect? This sets up a foundational paradox that modern science has wrestled with for decades. Why haven't we killed all mosquitoes? The reason isn't a lack of human will, and it definitely isn't a lack of cutting-edge tools. The real answer is far more counterintuitive. It's not that we lack the capacity to hunt them down. It's that we are facing a profound ecological and biological bottleneck designed by nature itself, one that humanity is forced to navigate with extreme caution. To understand the core of the problem, we first have to deconstruct a massive misconception in public thinking. When you get bitten and end up with an itchy red welt, you understandably think, "I hate mosquitoes." But in the dictionary of evolutionary biology, there is no such single entity as the mosquito. There are over 3,500 distinct species of mosquitoes inhabiting the planet right now. And here is the technical bottleneck of the entire equation. Less than 10% of those species pose any direct threat to human health. The major culprits belong primarily to just 3 specific genera: Anopheles, Aedes, and Culex. The vast majority of the other thousands of species are largely harmless to humans, living out their lives in remote ecosystems without ever interacting with a human being. Because of this, declaring a total war to kill all mosquitoes sounds incredibly satisfying when you're swatting at one. But scientifically, it's the ecological equivalent of dropping a nuclear bomb on an entire city just to eliminate a handful of specific targets hiding in a basement. Wiping out all mosquitoes wouldn't just eliminate the dangerous vectors. It would destroy thousands of species that pose zero threat to us, kicking off unpredictable ecological ripple effects. If we were to ignore the warnings and entirely erase mosquitoes from the global map, we would be stepping into an environmental guessing game. Consider the plant kingdom. Most people only notice female mosquitoes when they are hunting for a blood meal to develop their eggs. But between those blood meals, females and all male mosquitoes actually survive on plant sugars. In fragile ecosystems like the damp Arctic tundra or vast northern wetlands, Mosquitoes are frequent visitors to local flora, playing a documented, though not always irreplaceable, role in the pollination of certain orchid species. Then there's the food chain. Think of mosquito larvae, which live by the billions in freshwater bodies worldwide. In the natural world, they act as an abundant, easily accessible source of nutrients. They help sustain countless species of fish, amphibians like frogs and salamanders, and various migratory birds. But let's say we decided the risk was worth it. Historically, humanity actually tried a brute force method: widespread chemical warfare. In the mid-20th century, we blanketed entire regions with massive amounts of DDT, hoping to permanently erase malaria vectors. The result was a severe lesson in natural selection. Instead of going extinct, mosquitoes fought back with a terrifying evolutionary asset: a hyper-short life cycle and rapid genetic mutation. When intense chemical pressure hits a population, the rare individuals with resistant genetic traits survive and replicate at lightning speed, eventually building staggering levels of resistance that render standard chemical doses practically useless. On top of that, their reproductive biology makes manual eradication a statistical impossibility. Under the right environmental conditions, a female mosquito can lay hundreds of eggs in a puddle as small as a discarded bottle cap, with a life cycle that can move from egg to adult in a matter of days. However, this entire narrative has recently hit a massive, contradictory plot twist. Our failure to eliminate them is no longer due to a lack of technology. Because in laboratory environments, humanity has successfully engineered a molecular weapon capable of driving specific mosquito populations to extinction. This is the intersection of CRISPR gene editing and what is known as a gene drive. In standard biology, when two organisms mate, a modified gene from one parent has a 50% chance of being passed down to the offspring. It's like flipping a coin, meaning harmful mutations naturally get diluted and filtered out of the gene pool over time. But scientists figured out how to bypass this rule. By using a gene drive, the engineered trait actively copies itself into the opposing chromosome of the offspring. The inheritance rate jumps from a coin toss to nearly absolute certainty, pushing past 95%. When you release these gene-edited mosquitoes into a controlled environment, the trait spreads exponentially. A breakthrough study by Imperial College London demonstrated that in isolated laboratory cages, targeting female fertility caused a localized population to completely collapse in just 8 to 12 generations. We hold a genetic delete key, yet we hesitate to deploy it globally. Why the hesitation? The barrier is no longer just technological. It is an incredibly complex entanglement of biosecurity, international law, and a concept known as the eco-vacuum paradox. Let's assume we bypass the diplomatic nightmares and successfully eliminate Anopheles gambiae, the primary vector of malaria across sub-Saharan Africa. Millions of human lives could be protected. But nature deeply abhors a vacuum. When a highly optimized ecological niche is suddenly emptied, that massive pool of resources and habitat doesn't just sit there. Scientists worry that another organism will immediately rush in to fill the void. And this is the haunting question no model can answer with absolute certainty. What takes the throne next? Could an even more aggressive vector, like certain species of sandflies or ticks, rush into that empty space, carrying exotic, dormant pathogens that the human immune system is entirely unprepared to fight. Modeling these chaotic feedback loops strains even our most advanced predictive software. Furthermore, because wild animals do not recognize geopolitical borders, releasing a self-sustaining gene drive in one country means it will inevitably cross into another, making international consensus and global safety regulations an absolute requirement before a real-world release can ever happen. Because of these profound ecological and regulatory risks, the strategy in the war against mosquito-borne disease has completely shifted in recent years. The absolute goal is no longer to force a species into extinction, but rather to execute a highly targeted genetic reprogramming. This represents the front line of modern genetic research. Instead of trying to kill the insect, scientists are engineering mosquitoes so that their internal immune systems actively block the malaria, parasite, or specific viruses from developing inside their bodies. If the parasite cannot mature inside the host, the transmission cycle to humans is completely broken. The insect remains in the ecosystem, continues to fly, and remains a food source for birds and fish, but it is effectively disarmed. It is critical to note that this is not currently being deployed on a massive wild scale. It is an ongoing, highly scrutinized area of research being meticulously tested in isolated field trials and biosecure environments. Ultimately, the mosquito is no longer just a baseline nuisance. It acts as a profound mirror reflecting humanity's ultimate, yet volatile, power over the natural world. Confronting this challenge has forced our species to grow up. We are transitioning from a destructive force that flattens every obstacle in its path to highly cautious biological architects, species that understand that pulling a single thread can unravel the entire tapestry of life.